Okay, this is the second lesson regarding the equation. And see now, okay, so at this point, we said yesterday that these are the most important equation, 3 equation of equilibrium and 1 equation of storage, and 4 variable, the pore pressure and the displacement in x, y, and z. Regarding the deformations, because this is what we want to know in our, of course, soil, we have 2 cases in general. We have case of drained and undrained conditions. So let's say that, of course, in structural mechanics, we don't have these 2 conditions because we don't have water inside the material. But in this case, we have the condition of drained. So when our soil is fully drained, and in this case, there is no need to assess the excess pore pressure. So in this case, the problems are very simple because the consolidation is very fast and it can be neglected. For example, in case of foundation of a sandy subsoil, provided that the smallest dimension of the structure, which determines the drained length, is not more of a few meters. So the first case is very simple and can be represented with the equation that you already know from the other work, the other structural engineering course that you have already done. In the case of undrained conditions, when rapid loading of a soil of low permeability, for example, in a clay layer, the consolidation process needs to be considered since and there may be movement of the fluid. Therefore, in the following, we analyze the consolidation process under undrained conditions. So for now, we will consider the case of undrained conditions because these are the ones that, of course, as I said, are different from the one that you already know from previous courses. So again, the storage equation is the one that we already know, that is this one. And let's consider what happens if we consider a small amount of time. If the time is very small, we can consider this, the first 2 parts are the volume strain and the pore pressure immediately after the application of the load. While the term in the right-hand side represents the hand outward flux over the time interval delta t. When the permeability is very small, the time step delta t is also very small. This term will be very small and may be neglected. It follows that P0 is equal to minus alpha epsilon ratio SP, because we can, of course, consider only these 2 parts you can see. And at this point, we can also write that alpha epsilon ratio NCF plus alpha minus N per CS. That is SP as we introduced before in this way. Here we called SP, where it was here, and so we can define, let me see 1 second where is SP was. was defined here, see, n Cp plus alpha n alpha minus n Cs. And let's see, let's go back. Exactly. So at this point, this expression enables to eliminate the pore pressure from the other equation, such as the equation of equilibrium. So at this point, we can rewrite these inside this, and you can see that this part is neglected. And we can rewrite K, you see, and instead of K in general, Ku, that means under undrained conditions. So Ku is K when we consider undrained conditions. Ku is K plus alpha square ratio SP, and definitely is this values, and is the undrained compression modulus. It should be noted that these equations are completely equivalent to the equations of equilibrium of an elastic material. The only difference, of course, is the compression modulus K that is replaced by Ku. So definitely, if you remember that Ku is this with K plus this values, alpha squared ratio SP, we have definitely that these expressions are extremely common for you, that are the one that you already have here, that are the one that you already used in your, again, structural engineering courses. These equations also correspond precisely to the standard relations between stress and displacement from the classical theory of elasticity, as I said. Again, with the exception that K must be replaced with Ku in considering the undrained compression modulus. It may be concluded that the total stresses and the displacement are determined by the equation of the theory of elasticity, except that the compression modulus K must be replaced by Ku. The shear modulus G remain unaffected, so G remains G. This type of approach is called undrained analysis. In the flux and the particles are if the flux and the particles are incompressible, the storeactivity of the pore space SP is 0. In that case, the undrained compression modulus is infinitely large, which is in agreement with the physical basic of the original consolidation theory. If the particles and the fluid are incompressible and the loading process is very fast, non-drainage can occur. In that case, the soil must indeed be incompressible. In an undrained analysis, the material behaves with a shear modulus equal to the drain shear modulus, but with a compression modulus that is practically infinite. In terms of a stress modulus and Poisson's ratio, one may say that Poisson ratio eta is almost, the Poisson ratio nu is almost equal to 0.5 when the soil is undrained. So for undrained condition, we can consider something like what you already seen in structural engineering. Here, we can already consider a case, an example of a rigid circular foundation. For example, in the case of a semi-infinite elastic porous material as a soil, we can consider a foundation loaded with a total load P. According to the theory of elasticity, the settlement is like W infinite, that is P per 1 minus nu square ratio ED, where D is the diameter of the plate. This theory is from Timoshenko and Goodyear in 1970. P, of course, is the pressure, and E is, of course, the modulus. This is the settlement. See, that is infinite, of course, at the end, when no pore pressures are considered, or when all the pore pressure have been dissipated. So is at the end of the process. In terms of the shear modulus G and Poisson ratio nu, the formula may be written in this way. So you can see here that our settlement after the consolidation process, so after the consolidation has been completed, we have P that multiply 1 minus nu ratio to G per D, where G is, of course, the shear modulus. At the moment of loading, the material reacts with nu equal to 0.5, as we said. So the immediate settlement can be defined as W0 equal to P ratio 4GD. This shows that the ratio of the immediate settlement to the final settlement, so if we do the ratio between these two settlements, is 1 ratio to that multiply 1 minus nu. Thus, the immediately settlement is about 0.5 or the 50% of the final settlement or more, depending upon the values of the Poisson's ratio in drain conditions. So the consolidation process will account for the remaining part of the settlement, which will be less than 50%. And this is important because it gives us the possibility to study the consideration, the deformation of the rigid circular foundation. Another important problem is the Cryer's problem. That is a very, I think, deductive problem that we can see. For example, if we have a soil, a three-dimensional problem of consolidation, if we consider a sphere, a soil like a sphere, subjected to a pressure all around, with drainage to a layer or a filter material around the sphere. The solution of the problem can be was given the first time by Cryer in 1963 for the case of an incompressible fluid and incompressible soil particles. Here the general case will be considered, which is only slightly more complicated. So using the spherical coordinate R, which is appropriate for this problem with spherical symmetry, the storage equation can be rewritten with this formulation. You can see here that I'm using the spherical coordinate R. Well, in this way, we can have these, you can see that that comes from the drainage that is this. The only thing is that is rewritten into the spherical coordination. So here we can see that we can use this equation, and the volume strain epsilon is related to the radial displacement U by epsilon equal the sum of delta U ratio delta R plus 2U ratio R. The second basic equation is the equation of radial equilibrium, which can be expressed, of course, in this time as this delta R, delta sigma, sorry, ratio delta R, plus 2 times sigma R like minus sigma T ratio R. equal to 0. This is the second basic equation in the equation of radial equilibrium, which can be expressed in this way. At this point, where what are sigma r and sigma t are the total stress in radial and tangential direction. So it means that the total stresses can be separated into the effective stress and the pore pressure with these two equations that are, of course, the equation of the principle of Terzaghi. So we can rewrite the relation of the equation of equilibrium in this way, you can see here. And after writing this way, the same way, we can rewrite, of course, the first relationship that are these relationship. And we can, at the end, you can see here, express the equation of equilibrium in terms of the volume strain. So K plus 4/3 G ratio delta epsilon, right, ratio delta R is equal to alpha ratio alpha P ratio alpha R. In this equation, K is the compression modulus of the porous medium in fully drained condition, and G is the shear modulus. So this is definitely the equation of equilibrium that is expressed again in volume, in terms of volume strain. You can see here that we have the epsilon. So the epsilon remember what we said before, that epsilon is, of course, the sum of the three linear strains, and in particular is the delta V ratio V. I don't remember exactly. Let me see 1 second where we considered here. We said that we have delta V ratio V, that was epsilon here, see? So if we consider at this point the Kreyer's problem, we can remember that this is the final solution, the final equilibrium solution, and we have to impose, of course, the boundary conditions. So what is the boundary condition? We have two boundary conditions in the beginning, I mean at the center of the sphere when R is 0. And so we have that the derivation of P ratio R is 0, and U, the displacement is 0. And then we have two conditions at the boundary when R is equal to A, where we have P equals 0, and we have the strain, the stress that are 0 and Q. 0 if T is minus than 0, so before the consolidation problem, and Q is, of course, the flow when T is less than 0. So the first boundary condition expressed that there is no flow in the center of the sphere, and the second boundary conditions express that there can be no radial displacement at the center. The third boundary condition states that the accept pore pressure at the outer boundary of the sphere is 0, assuming perfect drainage. So remember that these are, please remember that these are, of course, very theoretical consideration. The fourth boundary, so this, describe the radial loading at the sphere circumference, and the radius of the sphere is denoted, of course, as A. So we can see here, so that we need, of course, we have four equations, remember, here, and we need, at this point, 4 boundary conditions to have, of course, our mathematical system fully determined. So, in the initial response, at the initial of the loading, there will be a response of the sample, which can be determined by considering the sample to be elastic with a modified compression, the modified compression modulo Ku can define, as we said, the solution. So this leads to a solution in which the state of stress is homogeneous, with all normal stresses being equal to the load Q. So the initial pore pressure at T equal 0 can be called like this: P equal P0, that is equal to alpha Q ratio alpha second plus KSP. That is definitely this parent of this. The initial volume change is then at T0 equal epsilon 0, like Q, so the flow ratio Q0, and is again parent of this, but with QSP. So here we can have both the P, so the initial pore pressure, and the initial volume change defined in terms of K and SP. It may be noted that the case of an incompressible fluid and incompressible particle, in the case, in other words, of CF and CS equal 0, and also alpha 0, in this case we have that P0 is like Q and epsilon 0 is like 0, indicated that in this case there is no initial volume change and the initial pore pressure is equal to the radial load. So that is, of course, a very, very small part of the big Cryer problem that we are analyzing. Wait a second. Okay, so at this point, we have to solve the problem. The problem can be solved in several ways. Now, I don't want you to bored so much with the analytical problem. I never ask this solution because it is based on Laplace transformation. But the pore pressure can be defined with the Laplace transform, where ES is the Laplace transform parameter. And so if we consider P underscore with, as I said, a Laplace transformation, we can have that P is equal the integral from 0 to infinite of P that multiply the exponential of minus s, that is the Laplace transform parameter, t, that is the time in the t. The transformed basic equations can easily be solved involving 4 integration constants, which can be determined using the boundary conditions. So we have 4 integration constants, and we need these 4 boundary conditions, of course, as I said. So I don't want to go on, as I said, with the mathematical background, also because it required a lot of mathematical tools, but at the end, the final expression of the Laplace transformation of the pore pressure can be may be founded as this, you see, pretty complicated expression where lambda square is beta s ratio c, and there are a couple of other parameters where you can see c is this ratio, beta is this sum, and m is this. I don't want you to know all of this, of course. The only point is that when you know these this equation that is put together with the boundary conditions, 4 boundary conditions, because we have 4 expressions, we can 4 equations, so we can derive and define all these let's say, the final expression, all these parameters that help to define the pore pressure. Just a little clarification, the coefficient C is the usual coefficient for solidification, for consolidation, and is, you can see, something that you already know, sort of sense, because is K that multiply K plus 4/3 G. Be careful that this K is not the same K. One is the stiffness, the other one is the permeability. Gamma W, of course, is the water coefficient, weight, the water weight, the specific weight. In the case of an incompressible fluid and an incompressible soil particle, for example, the one derived from Cryer in 1963, the Biot coefficient, as already said, is alpha equal 1. The pore space store activity SP is 0. So this part is 0 and this part is 0. So what does it mean? That beta is equal 1 and M is this relationship. That is, of course, a particular case of a more generalized case. Of particular interest is the pore pressure in the center of the sphere, or in other words, at R equals 0, that is denoted as PC. And the Laplace transformation becomes this. That is, as you can see, very similar to this one in case of R0. So this term is different. And B approximate at this stage to verify the initial condition using the fundamental property of the Laplace transformation, where the limit for t to 0 is equal to the limit of S infinite, respectively for P and SP. I don't want you to concentrate on this, but at the end, this gives that P0 is equal to Q ratio alpha that multiply 1 plus KSP ratio alpha square. So this is the pore pressure that can be implemented inside the inverse Laplace transformation equation. And at this point, we can have, you can see PC ratio P0. Again, I don't want you that you memorize all this sentence, all this equation, but what I want to say is that, first of all, the coefficient Xy have the positive roots of the equation, are the positive roots of the equation, and this solution agrees with the solution obtained by Cryer in 1963 for the case of an incompressible fluid and incompressible particles. But I would like you to take a little bit more into consideration, more attention to, is this what happened to the pore pressure in the center. So if we put PC ratio P0 in the y-axis and CT ratio alpha second alpha square in the x-axis, we can see the result of the three values of the Poisson ratio, I mean 0.5, 0.25, and 0, assuming that pore pressure and the particles are incompressible. So in the case, as we said here before, that here in the case of the incompressible fluid and incompressible fluid particle, the case that was considered by Cryer in 1963, and in the case of the Biot coefficient alpha 1 and the pore space store activity SP0. So it's a very specific case. It is interesting, otherwise, to note that the various values, especially the 1 minus 0.5, the pore pressure in the center of the sphere initially increases before it is ultimately reduced to 0. So first, for smallest values of CT ratio alpha square, there is an increase, and this increase is bigger for smaller values of nu, of Poisson, while after a certain time, a certain value, there is a decrease in the values of nu. This is caused, of course, by the drainage, which start, of course, at the outer shell of the sphere and which produce a tendency inside the sphere. So this leads to an additional compressive stress on the practical incompressibility core of the sphere, so that an additional pore pressure is generated. So this increase that depends definitely on the Poisson ratio, is generated from the drainage. This is what it is important to consider, of course. It is also important to consider one important thing, that that definitely if we have the general condition of a soil with between 0.5, 0.4 or something, we are around here. So there is not a big increase caused due to the drainage, but it is important to consider. The effect can be considered as a consequence, as we said, of the practically immediate transmission of the static stresses and the gradual progress of the diffusing process of underground flow. A similar effect was obtained also in 1953 by Mendel for the problem of a clay sample compressed between two rigid plates with lateral drainage. The effect is usually called the Mendel-Cryer problem or effect. It has been confirmed experimentally by Gibson and al. In 1963 and even later in 1963 by Verret. So this is definitely what I'm more interested in, except for all the analytical background. It is important, otherwise, that if we consider, again, the general system of equation of the three-dimensional consolidation, the storage equation together with the three equations of equilibrium has to be solved together, and they are unfortunately coupled. So if we are in linear conditions, is even simple, but if not, we are in a very formidable change, very difficult, challenging task. As it seems worthwhile to try to simplify this procedure. So at this point, we can see something a little bit different, a little bit more convenient. In fact, if in the storage equation, the first term can be eventually represented by C that multiply the derivation of P inside the T, the time, where C is somehow constant, because at this point the equation can be reduced to a very simplified form, because see here, if we put this inside the derivation of epsilon, we can have alpha plus C, because this, of course, is alpha plus C, plus SP, that all multiply the derivation of the pressure in the time. And this is, of course, the classical, what is called the classical diffusion equation, for which many analytical solutions are available. And in this case, the system of equation is uncoupled. I can tell you that if we are talking about linear equations, it's not impossible that we can solve even this solution. But of course, the system of equation is a little bit simpler if it is uncoupled. So I would like you now to show case 1 and case 2 before going to the Terzaghi problem, and I will show you a very nice problem. So let's see a little bit what I call case 1. So we have two possibilities of uncoupling of the soil. The first possibility is to obtain the volume epsilon is a function of the effective stress sigma comma. So if we consider that for a linear material, this relationship, as we said, can be rewritten with epsilon equal to the compressibility, that is 1:k, that multiply the isotropic effective stress minus the sign that is needed because of the different sign convention used for stress and strain, in particular for compression. We can write that the effective stress is the difference between the total stress and the pore pressure, if we, of course, consider the bias coefficient. And thus, one may write epsilon equal to minus Cm that multiply sigma minus alpha p. Differentiating this, if we do the differentiation, let's say derivation, with respect to time, we can see that if we consider what happened to the epsilon during the time, we can derive this expression by considering, of course, the derivation of the differentiating of the stress with time and the P with time. We can define at the first approximation that isotropic total stress is constant in the time, as we said. And then we can rewrite the equation with this equation, alpha square Cm plus Sp, ratio P in T, that is, of course, this first part plus this, equal to, of course, the what we already know. So in a sort of sense, we are rewriting this, you see here, by rewriting this first part. So this term remain the same. This term remain the same, but what we are modifying is essentially the derivation of epsilon ratio alpha t, which is indeed a diffusion equation. This assumption is again simplifying and was firstly suggested by Renduling in 1936. And the isotropic total stress at this point may be constant in certain cases, but I mean, is not unrealistic. So in many cases, consolidation may take place while the loading of the soil remain constant. So when we have a constant load, the consolidation can take place. And although there are sort of redistribution of stresses, we can theoretically assume that the total strain, the change in total stress is approximately small. And this condition, even if they are difficult to demonstrate, they are they have a good approximation, let's say. In this way, considering these assumptions, various solutions of coupled three-dimensional problems have been obtained in many cases. For example, a certain difference with the coupled solution have been found. So we can define, in effect, which kind of solution we can consider. And sometimes there is even a very pronounced difference in behavior for small values of time, in the sense that sometimes the pore pressures initially show a certain increase before they dissipate. So, if this case was the uncoupled consolidation, case 1, in case of a constant isotropic total stress, we can see a second case that is another class of problems in which instead the uncoupled analysis is justified in case in the case of the horizontal deformations negligible and vertical total loss remain constant. So if we have horizontal deformation that are not really big, but we have only vertical total stresses, we can, in effect, consider that the deformation are horizontally confined. In this case, we have a large horizontal extension. We need a very horizontal extension that, in general, in a soil is good, because generally soils have an infinite extension, especially horizontal. When soils are loaded with a constant surface load. And again, this may be acceptable. And if the horizontal deformation are set equal to 0, it follows that the volume strain is equal to the vertical strain. So epsilon x and epsilon theta, and epsilon x and epsilon y are 0. So if we go back, we have that the deformation along this axis and this axis are considered 0, and therefore we can consider, let's see here, wait a second, and consider that for linear elastic material, the vertical strain may be related to the vertical effective stress. So not only we can write that the volume strain is equal to the vertical strain because all the others are 0, but since we can consider that everything, the material is linear elastic, we can introduce what we call the vertical compressibility of a laterally confined soil sample, and we can write epsilon in this way. But since epsilon has inside, of course, the pressure, the stresses, the effective stresses, we can use, of course, Terzaghi again principle. So we can write, instead of sigma first zeta zeta, sigma zeta zeta minus alpha p. And therefore, at this point, we can derive this formulation, and we can into the time, and we can obtain the epsilon ratio delta t, that is minus mv, that is constant, and these two ratios that are the ratio in the stresses. But these two ratio in the stresses are very interesting because we can substitute inside this formulation. So at this point, we can rewrite everything only in terms of P and sigma theta. So you can see here that introducing this relationship among deformation and stresses allow to introduce to derive, let's say, a very condensed formulation that consider the final equation of uncoupled consolidation pretty easy. Again, this is indeed of the form of a diffusion coefficient if the vertical total stresses is constant. It may be concluded that in the case of zero lateral deformation and constant vertical total stresses, the consolidation equations are uncoupled. If the medium is homogeneous, the coefficient K ratio gamma W is constant in space, and the differential equation can be reduced to this very, very simple relationship. So ratio, let's say velocity of application of the pressure is equal to the gradient square of the pressure multiplied by CV. This gradient, this operator, is the Laplace operator. You can see that it's a gradient square, definitely, while CV is what we introduced, the consolidation coefficient. Remember that we talked previously about MV as the vertical compressibility that has not to be confused with CV, that is a little bit close, but let's say that it depends on several things. First, it depends of K, it depends of alpha, MB, and SP. So this form was first derived by Terzaghi in 1925 for one-dimensional case of flow and in vertical direction, because he obtained this in a compression test in laboratory, or in the consolidation of an extensive clay layer in the field, loaded by an uniform surface. It was also derived by Jacob in 1940, but again, it was for some, let's say, very isolated case. And I mean, it used different notations and was an aquifer of thickness H, transmittivity T, and stochasticity S. Anyway, in that case, the consolidation coefficient was T ratio S. What I want to say that if we are in case 2, as we say, and if we do all the simplification that we have done, we will be able to solve, now I will explain how, what we call the Terzaghi problems. And this is really a very interesting application. So let's remember this, that is, again, valid for a medium that is homogeneous. And so we can write here the problem first solved by Terzaghi in 1925 for a thickness layer of 2H, which is loaded, you can see here, at time t equal 0, for a load that we call Q. The upper and lower boundary of the soil layer are fully drained, so that along this boundary, the pore pressure P can be considered 0. So at this point, we can write our differential equation for this case as a fully one-dimensional form of the one that we already seen. And so at this point, we can write this instead of the bigger one. And since at the moment of loading, there cannot yet have been any fluid loss from the soil, we can easily consider that the conditions, the initial condition of the pore pressure, again at T equal 0, consist of P0 equal alpha mv ratio alpha square mv plus sp per q, where q is again the load. So if the fluid and the soil particles are uncompressible, alpha equal 1 and sp equal 0, again as Biot says, so that p0 equal q, as Terzaghi consider, the boundary conditions are for zeta 0 p equals 0 and for zeta 2h p equals 0. So we can say that the problem is potentially solved by using the mathematical tools supplied by the theory of the partial differential equation. For example, by using the method of separation of variables that was proposed by Willy in 1960, or even, if you want, again, the Laplace transform method. I'm not entering again in details, but what I want to say is that we have this equation and these boundary conditions. So let's see what happened. So we again use the Laplace transform for the pore pressure, and we can transform the differential equation using the initial condition as this. So the partial differential equation now can be reduced to a very simple differential equation by introducing the boundary conditions. At this point, we can write, I'm skipping some passage, the inverse transform of this equation by considering the complex inversion integral. I don't want, again, to enter in too many details, but at the end, we obtain this formulation. You can see here the ratio of P0 defined with all these sum. This P ratio P0 is similar to what we already have previously here. Remember, PC ratio P0, this is another kind of problem. And at this point, we can write and we can derive, and I'm more interested in showing this, the analytical solution of the Terzaghi problem. And here we have to discuss a little bit more. So if we look at the figure, we have that for increasing values of CVT ratio H at the second, you can see from 2, 1, 0, 5, 0, 2, 0, 1, 0, 0, 3, and go and on. We can see what happened for P ratio P0 and Z ratio H. So we can have several considerations, but what we want to say is that, of course, there are some simplification. For example, the number of terms was chosen such as the argument of the exponents function was less than -20 of this exponential here. And so the factor exponential -20 is disregarded. The figure show that the solution satisfy the boundary conditions, see, here and here, or for zeta equal to at the top and at the bottom, but it doesn't show, of course, that it is the correct solution. That can only be shown by the analytical formulation that we presented before. So, but anyway, what is interesting, it is to see how P ratio P0, or these values, can be represented inside the height of the layer. So we can see here how the pressure increase in relation with P0. inside the 2-8 layer. So coming to our problem, we can calculate the settlement by noting that the strain is determined by the effective stress. So epsilon, as we said, can be named as minus mb that multiply sigma z less alpha p, and the settlement, as we said, is the integral of the strain over the height of the sample. So we can derive this value inside the integral between 0 and 2h. And at this point, we can, of course, as we already seen, introduce this terminal inside here. The zeta is definitely constant to the zeta, and we can define the first part that is almost constant, minus this part that depends only on p zeta. So the first term in the right-hand side is the final settlement, this, which will be reached when the pore pressure are being completely dissipated. This value will be noted by V infinite. Excuse me, it is this this part, because these can be considered depending on pore pressure. But when pore pressures are 0, this part, of course, is 0. So this value can be, as we said, called W infinite. That means that the pore pressure are dissipated. And immediately after the application of Q, load Q, the pressure, of course, is equal to P0. This means that immediate settlement at the moment of loading is V0 equal, we can see here, 2 mVh that multiply Q minus alpha P0. So see, this part is, of course, equal to P0. So again, is constant, and so this part can be called alpha mVh double H per P0. So introducing this constant inside the total calculation, we can have W0 equal this. And in order to describe the settlement as a function of time, is most convenient to introduce what we call the degree of consolidation. That is the ratio between the actual values of W minus the displacement in the beginning, ratio the difference between the total displacement at the end when the pore pressure is completely dissipated, the final settlement, and the initial settlement. This U, consider that is very important because it gives the ratio between the actual relative, let's say, settlement among the total settlement that can happen inside the layer of the soil. And this quantity, of course, can vary between 0 when we are loading, so in the beginning, to 1 after the finishing of, after the consolidation is finished. And at this point, we can introduce this U inside the expression given above, and we can relate the pore pressure with U in this way. So if we introduce P0 inside this C integral, we can write U as 1 ratio to H that multiply this, integral, where P0 minus P ratio P0 per dz. Of course, again, this P depend on the pressure inside the layer. So the final expression of the degree of consolidation as a function of time can be defined in this way, and we can use U with, we can introduce, U inside this representation, and we can, at the end, define the degree of consolidation as a function of time. So here we can see that, we can see how many parameters are entering inside U. Again, U, remember, is the degree of consolidation. So is 1 minus all of these. Of course, if T is infinite, it means that all the pore pressure are dissipated, and so U is equal 1. Of course, on the other side, if T is equal 0, it means that all this part is 1. So again, U is 0 because the degree of consolidation is nothing, 0. But the terms in the infinite series have to pi greco second ratio 8, as we said, is the final value of this. And if we eliminate pi greco square ratio 8 per 2 ratio pi greco square, all this is 1. A graphical representation of the degree of consolidation as a function of time can be shown in this figure, and I want a little bit to stop and discuss. Let's take some water first, because I'm like a soil, I need water sometimes. So, here what we have. We have in the x-axis the degree of consolidation. As we said, is CV per T, so it depends on T, ratio 8 squared. 8 squared, again, is the layer height, T is the time, and CV, of course, is the compressibility, while U is the degree of consolidation. So we can see here that if we go, wait a second, I would like you to show what we said here, because it this. We see that here we were talking about what happened when we increase the values of CVTH square. That was definitely the transformer differential equation. See this we introduced here. And in particular, remember that we consider what we started was the differential equation in the case of a fully one-dimensional form. It came again from this, okay, where again this is the Laplace operator of P multiplied for the consolidation coefficient, that is equal to the differential of P in time. So what we can see there instead is what happened here with the degree of consolidation. Definitely we are talking about time, except for CV ratio 8 second, the consolidation coefficient and the height of the layer, and what happened for U, where U is the degree of consolidation. So we can see that if we increase time, the degree of consolidation decrease. And again, for T equal infinite, we are here, and U is equal 1. When we have T equal 0, U is almost 0, because these two terms are 1 minus 1. So we can, in other words, say that the presence of the consolidation in a soil allow to dissipate water, and we have the degree of consolidation that increase during the time. So we can say that the history of a soil can be defined by the degree of consolidation. The more soil is consolidated, or the bigger U is, the more close to 1 is U, the more it means that the water is dissipated. The more U is close to 0, the more means that time, the degree of consolidation is 0, the more it means that time is 0. It means that we still have a lot of water inside the soil. So, in order to conclude and define this, again, settlement, we can importantly say that, theoretically speaking, the consolidation phenomenon can be considered finished only when t equal to infinite. For all practical purposes, it can be considered as finished when the argument of the exponential function is the first term of the series. Excuse me, in the first term of the series, this is around 4 or 5, or in other words, where we are here, around 2. So here. CVT ratio H2 is around 2. It is a very useful formula because it enables to estimate the duration, as I said, of the consolidation process. So it is a formula that helps to understand what is the consolidation of the soil that we are considering. It also enables to evaluate the influence of the various parameters on the consolidation process. For example, if the permeability is twice as large, the consolidation will take half as long. So it is also a good estimation of the time of consolidation. If the drainage length is reduced by a factor of 2, the duration of consolidation process is reduced by a factor of 4. So this is also really interesting because this formulation allows to give some estimation. This explains the usefulness of improving the drainage in order to accelerate consolidation. And this is a very interesting thing, and it comes as a response, an answer of the question that some of you posed to me in the first lesson. Somebody asked after I said I gave an example of a road. They asked me what happened in the case I need to build a road and I have water. We have to use drainage, but how? If we want to accelerate consolidation, it is useful to increment drainage on the basis of these findings. In a thick clay, for example, drainage can be really effective. For example, by installing vertical drains, since the drainage length is reduced by the presence of the drains, and the more that the drains are close each other, and of course the best it is. As the consolidation is proportional to the square we can see here of the drainage length, it may be extremely effective in reducing the consolidation time and thus accelerating the subsidence due to the construction of an embankment. So what we are talking here is that when we are in a design consideration and we are constructing, for example, roads, embankments, whatever soil system, we have to consider consolidation. Consolidation is not a problem that finish with a very limited time, because it depends on several parameters, as we saw. So, for example, it depends on CV. CV, as we said, depends where it was CV. Let me see 1 second. On K, SP, MB, alpha, gamma V. Gamma V can be considered constant, but the other not. The other depends on the parameters of the soil. So depending on which typology of the soil, we can have several consolidation process. As we said, generally the consolidation is more difficult for clays. So depending on which kind of typology of soil do we have, we can consider several settlements. And so how we can improve our condition? We can improve, especially in clays, to put drains for accelerate the consolidation process. So again, it's not necessary that you know all these, I never ask all these kind of equations, but again, it is really, really important that you understand first this concept that we call here, that it is important to consider what happened inside inside a soil, especially very close to the center, and what happened instead at the distance. But especially is important here to consider what happened if we have a consolidation problem of whatever system, geotechnical system, in particular the solution of the Terzaghi problem here, when we see the dependence with this term, that is CVT ratio H at the second. And in particular, this as last thing, when we can see that depending on the property of the soil, we can have different degree of consolidation. So thank you again. Again, if you have some questions here, I will answer on Tuesday, or you can send me email also. And so I think now that we can stop here the presentation. Maybe I was a little bit fast today, but yeah, you have time. Sorry for this, but at the beginning there was some noises here, so sorry again for this, but I'm trying to, again, condense all this thing in order to allow us to do some nice applications, nice exercises in the next day. But what I want to show now, just before closing, is a little bit to sum what we said all together. So here we started with the consolidation process, and we saw that all these are the expressions that we need to define the consolidation process. Then we introduce a simplification with the Terzaghi principle, that, remember, that is only an approximation. Terzaghi is a principle, not a theory. That is this, and it is important that you remember this formulation. Then we consider the conservation of mass, and we introduce inside the conservation of mass this formulation, the Darcy law, in order to obtain a very interesting storage equation, that is this one. This one is the storage equation that where the Darcy law is introduced. Then we rewrite the equilibrium equation, as you know, from structural engineering, with the storage equation included. You can see here. And we discuss the fact that we need several components, several variables. Our variables are these four, so 4 variables, and of course we need 4 boundary conditions. So we did the 2 cases of drained and undrained condition. We defined that the drained condition definitely is something that are very close to what you already seen in the past in structural engineering, while the undrained condition is what we really want to know. And in general, we are talking about, remember, clay layers, because we are talking about low permeability. Then we introduce these terms, but we did that except for the undrained compression modulus that is a little bit different from K, there is nothing very different from what you already seen for structures. But what is really important is to define this, that is the final settlement. So the final settlement after the consolidation can be, for example, derived with acquired problems, and we again derive after putting the boundary condition this case, and again you can remember all the things that we said with the increase due to the Poisson coefficient. And then in the case of especially case 2, we introduce another simplification that consider CV as the consolidation coefficient. Here we introduce the final problem, but it's really, really important, and we will use in our examples, in our exercise, the Terzaghi problems, where this formulation is defined in terms of pressure in the time and pressure in the space. After some consideration, we obtain the analytical solution of the Terzaghi problems that again depends of CVT ratio H2, and then we define the settlement. Again, I'm not interested that you know all the passages, but it is fundamental that you understand the global meaning of what we are doing. And again, we will apply all of this in the next exercise next week. So now let me like this. So thank you so much for this to attending this lesson as well. And now I interrupt the recording, and see you next time. Thank you.